Hello everyone, welcome to this lecture. So, in this lecture we will continue our discussion on cryptography and we will see some more applications of the concept from number theory and abstract algebra in the context of cryptography. Namely, we will see the definition of public key crypto system and we will see two very popular instantiations of public key crypto system, namely that of ElGamal encryption scheme and RSA encryption scheme. So, let us start with the definition of public key cryptography. What exactly is public key cryptography, why exactly we need that and so on. So, this is the Diffie-Hellman key exchange protocol which allows two parties Sita and Ram to talk over the internet publicly and agree upon a common key k, and if we perform all the operations over a sufficiently large group where a random instance of discrete log problem is very difficult and any third party in a reasonable amount of time will not be able to come up with the value of key that Sita and Ram have agreed upon. Okay. So, even though this is a very breakthrough result, because before the invention of the Diffie-Hellman key exchange protocol, people simply thought that it is not at all possible to solve the key agreement problem, but now Diffie and Hellman showed that indeed it is possible to agree upon a key by talking publicly. But the downside of the Diffie-Hellman key exchange protocol is that it requires both the parties to be online. So, imagine the two parties in different time zones, then it hinders the spontaneity of applications like email. So, for instance, if Sita and Ram are in two different time zones and Sita wants to send an encrypted mail to Ram, then Sita will initiate a Diffie-Hellman key exchange protocol instance with Ram. She will send her message, namely g to the power alpha to Ram. But now it might be the case that when g to the power alpha is delivered to Ram, Ram is sleeping because Ram is in a different time zone. Until and unless Ram also gets up and communicate back g to the power beta, Sita cannot use the key g to the power alpha beta for encrypting her email. So, in that sense the spontaneity of the application is lost here, right. So, that is why to get around this problem, Diffie and Hellman proposed an architecture for a new type of crypto system which is different from symmetric key crypto system. So, remember the symmetric key crypto system, the same key is used both for encryption and decryption, right. So, we were looking for a mechanism where the key g to the power alpha beta will be used for encrypting the email as well as for decrypting the email. But Diffie and Hellman were thinking about a new form of cryptography and today we call such crypto systems, such forms of such form of cryptographic algorithms as public key cryptography, public key crypto system. So, let us see the architecture of public key crypto system. So, in this system the receiver will have two keys, a key which we call as public key pk available in the public domain, and there will be another key sk which will be secret key and available only with the receiver. Now, in this system any person who wants to encrypt a message for this receiver will look for the copy of the public key in some public domain, may say for example, a telephone directory or the home page of the receiver. Once the public key copy is available to the sender and sender has the plain text M, he will use the encryption algorithm and produce the cipher text or the scrambled text which is communicated to the receiver. Receiver upon receiving the scrambled text will now use a different key, namely the secret key which is available only with the receiver, and he will decrypt and recover back the message M. Okay. And now the security property that means that we require here is that if there is a third party, an attacker who knows the description of the public key, who knows the description of the encryption algorithm, who knows the description of the decryption algorithm, and who also knows the description of the cipher text, should not be able to figure out what exactly is the underlying message, because the secret key is not known to him. That is a loose security property that we require here. Okay. So, the analogy that I can give here is the following. You can imagine that receiver has created multiple copies of a padlock, all of which can be opened using a single key. and now the public key is nothing but copies of that padlocks, but in an open state. If I am a sender and I want to communicate some message secretly to the receiver, what I will do is I will take one copy of that open padlock, I will take the message and keep it inside a box, and now I will lock the box using that padlock by pressing the padlock. So, that is equivalent to saying that I have encrypted my message. Now, when that when that locked box reaches the receiver, receiver has to open the padlock, and that he can do by using the secret key which is available with the receiver. So, that is the analogy, and this is different from your symmetric key crypto system, where both sender and receiver were using the same key for opening the locked box as well as for closing the locked box. So, for the moment, just imagine that we have a public key crypto system, namely we have an instantiation of public key crypto system, but even if I assume that we do not have an instantiation of public key crypto system, if at all this architecture is realizable, it has got tremendous potentials. It has got tremendous potentials in the sense that now the whole problem of key distribution is easily solved. If I am a receiver, I do not, and if I am Amazon, say for instance, I do not have to worry who is the potential sender. He can be any entity from the world. Whoever wants to communicate with me, I just have to publish my public key for him, which I can do once for all, and then anyone who wants to communicate to me has just have to use that public key, encrypt the message and communicate to me. So, in some sense the problem of key agreement is solved, and I do not need to have a dedicated secret key with each and every entity in this universe. I will just have a secret key, and the corresponding public key can serve the role of the encryption key for every potential user with whom I want to do a secure communication. So, even though Diffie and Hellman thought about this architecture, this new system, they failed to give a concrete instantiation, namely a concrete encryption algorithm, concrete decryption algorithm, a concrete mechanism of coming up with the public key and a concrete mechanism of coming up with the secret key. And the race for coming up with the first instantiation of public key crypto system was won by another Turing Award winner triplet, namely RSA, which we will discuss very soon. But the interesting feature here, interesting fact here is that even though Diffie and Hellman failed to come up with a concrete instantiation of our architecture, it was hidden in their it was hidden in their key exchange protocol itself. It was so. What we are going to do next is we will again recall their key exchange protocol, the Diffie-Hellman key exchange protocol, and then we will see that how by doing a minor tweak, a minor modification to the key exchange protocol, we can get an instantiation of public key crypto system. But unfortunately, Diffie and Hellman failed to realize that. Okay. So, this encryption scheme is called as ElGamal encryption scheme, attributed to Tahir ElGamal, who made this very crucial observation regarding the Diffie-Hellman key exchange protocol and what exact modification needs to be done. So, this was the Diffie-Hellman key exchange protocol. Sita sends her mixture, namely g to the power alpha, Ram sends his mixture g to the power beta, where alpha and beta are individual components picked by Sita and Ram, and the final key is g to the power alpha beta. Now, the whole process can be visualized as an instance of public key encryption scheme as follows. The intuition is the following: if g to the power alpha beta is a common key which is going to be agreed upon between Sita and Ram, and we know that if the discrete log problem is difficult to solve in my group, then any third party who has monitored the communication will be unable to compute g to the power alpha beta or the key k in a reasonable amount of time. Then I can use the same key k for encrypting the message. So, for instance, if Sita is the receiver and Ram is the sender, and if sender is having a plain text M, and again imagine that it is an element of the group G over which all the operations are performed, then what sender can do is the following: it can use the key k, namely g to the power alpha beta, for masking the message, right. And by masking the message, I mean here that perform the group operation between the plain text, which is a member of the group, and the key k as well, where the key k is the element of the group as well. Okay. So, that will give another group element, denote it as C. So, C will be the encryption of the message. And now, how Sita can decrypt back the plain text? So, for recovering the plain text, Sita has to unmask the effect of key, because the message is been masked with key. So, if the key is unmasked, the effect of mask will go away and Sita will be able to recover back the plain text. And for doing that, unmasking here is nothing but taking the element C and performing the group operation with C and the inverse of k. Because if I perform the group operation on C and inverse of k, then the effect of k and k cancels out, and what I will be left with is the plain text M, which sender want to encrypt. Okay. So, now let us see the whole thing as an instance of a public key crypto system. Okay. So, this was the message which sender. So, I am treating Ram as the sender here and I am treating Sita as the receiver. So, the crucial observation of Tahir ElGamal was the following. I can imagine Sita or receiver sending her contribution for Diffie-Hellman key exchange protocol once for all for every potential sender. So, right now what is happening is, depending upon Ram, Sita was picking alpha and contributing g power alpha. So, if there are multiple Rams, she will be picking multiple alphas, independent alphas, and will be sending g to the power alpha 1 to first Ram, g to the power alpha 2 to the second Ram, and so on. The key observation here is that do not do that for every potential Ram. In fact, it is not even required that who is going to be Ram. Let receiver or Sita start executing her instance of Diffie-Hellman protocol once for all. Namely, whatever is her contribution for the Diffie-Hellman key, and what exactly I mean by contribution? Her contribution was g to the power alpha, right. So, you can imagine that in the Diffie-Hellman key exchange protocol there are two contributions, contribution g to the power alpha coming from Sita's side, contribution g power beta coming from Ram's side, and both these contributions were somehow combined to get the overall key g to the power alpha beta. So, what ElGamal proposed is that let receiver makes her contribution public once for all, namely she picks some random alpha as her secret key and make g to the power alpha available in the public domain as her public key. So, it is as good as saying that she is declaring publicly that okay, I will not be again and again participating in different instances of Diffie-Hellman key exchange protocol. Whoever is going to be Ram, just think as if I am going to send g to the power alpha to you if I would have participated in the Diffie-Hellman key exchange protocol. That is the way public key and secret key will be picked by our receiver. Now, imagine there is a sender Ram who has a plain text M. He wants to encrypt the plain text M. How he can do that? Ram will now do his part of the Diffie-Hellman key exchange protocol, namely he will give his contribution, which is g power beta, and now Ram knows that once he sends g to the power beta to Sita using g to the power alpha, which Sita anyhow has made public, and treating g to the power beta as the message coming from Ram, Sita will be able to compute the key g to the power alpha beta. So, what Ram can do is, once he has sent g to the power beta, he can use k, namely g to the power alpha beta, for encrypting the message, and the overall encryption of the plain text will be now two messages. The first message will be Ram's contribution for the Diffie-Hellman key exchange protocol, and the second message is the actual encryption of the message. How Sita will be doing the decryption? So, this is the encryption process, sending his contribution of Diffie-Hellman key exchange protocol and then masking of the message. This whole thing can be visualized as the encryption of the plain text. The decryption happens as follows: Sita computes the key k, assuming that Ram has participated in an instance of Diffie-Hellman key exchange protocol. So, she will be able to compute g to the power alpha beta. So, for that she has to take her secret key, and raise that secret key. She has to take the first component of the ciphertext, namely C1, and raise it to her secret key, which will give her the common key g to the power alpha beta. And now she can unmask it by taking the second component of the ciphertext and performing the group operation with k inverse, where k inverse she has computed in the previous step. So, that will be the decryption process for Sita. A very cool observation, which unfortunately Diffie and Hellman missed, okay. And that is why Tahir ElGamal got whole credit of inventing this crypto system. And now, why this whole process, whole mechanism will be a secure mechanism. So, imagine there is a third party, Ravana. Will he be able to find anything about the message M in the reasonable amount of time? Well, the only way he can learn anything about the message M is by learning the key k. But for learning the key k, he has to actually attack the Diffie-Hellman key exchange protocol, or he has to solve instances of discrete log problem. So, assuming that solving random instances of discrete log problem is difficult, this whole process is indeed an instance of public key crypto system. So, now as I said earlier that the race for coming up with the first instantiation of public key crypto system was won by another Turing Award winner triplet, namely RSA, Rivest, Shamir and Edelman. So, now let me give you briefly the description of the RSA public key crypto system, again which is based on several interesting results from number theory that we have discussed till now. So, let me recall the group Zn star and some concepts related to the group Zn star. So, recall the definition of Zn star is the collection of all the values in the range 1 to n minus 1, which are co-prime to your modulus n. Okay. So, for instance, the set Z10 star will have the elements 1, 3, 7, 9. It will not have the element 2 because 2 is not co-prime to 10. It will not have the element 4, it will not have the element 5, 6, 8 because all of them are not co-prime to 10. It turns out that if your modulus n is a prime, then Zn star is nothing but the set 1 to n minus 1. And we already proved in one of our earlier lectures that the group Zn star along with the operation multiplication modulo n constitutes a group. So, the order of this group Zn star, namely the number of elements in the set 1 to n minus 1 which are co-prime to n, which is also the order of the group Zn star, is called as the Euler-Totent function, okay, denoted by this phi of n function. And there are formulas for calculating the size or the order of the group Zn star depending upon the value of n. So, the interesting cases are the following: if n is a prime number, then the order of the corresponding group Zp star is p minus 1, or equivalently there are p minus 1 elements in the range 1 to 0 to p minus 1 which are co-prime to p. Whereas, the case which we will be using in the context of RSA crypto system is when n is the product of distinct prime numbers p and q. So, if n is the product of distinct prime numbers p and q, then the size of the group Zn star is p product of p minus 1 and q minus 1. And this can be proved using the principle of mutual inclusion exclusion that we had discussed in one of our earlier modules. So, if you want to verify this, consider n equal to 10 which is the product of 2 and 5, and then we know that there are 4 elements in Z10 star, namely the order of Z10 star is 4. So, I should get that phi of 10 is 4, and indeed phi of 10 is 4 because it is 2 minus 1 multiplied with 5 minus 1. And we know that if I take any element a in the group Zn star, then a to the power phi of n modulo n is 1, and this can be proved in multiple ways. I can use the following result from abstract algebra. I know that the order of the group Zn star is phi of n, because that is what is the definition of phi of n, and the element 1, the numeric element 1, the numerical 1 is actually the identity element of this group Zn star. And I know that you take any group element irrespective of what is the order of that group element, a to the power order of the group will always give you the identity element, right. So, phi of n is the order of the group, A is an element. So, it does not matter what is the order of A, irrespective of whatever is the order of A, I know A raised to the power order of the group is 1 and A raised to the power order is nothing but A to the power phi of n. Now, based on this theorem I can say the following: if I want to compute A to the power x modulo n, then in the exponent I can perform modulo phi of n, because I can rewrite A power x as several blocks of A power phi of n, A power phi of n, and like that, and the last block consisting of A power x modulo phi of n. Each of these blocks with A power phi of n will give me the identity element 1 1 1, and I will be left only with the last block which has A power x modulo phi of n. So, now let me introduce RSA function, which forms the basis of RSA public key crypto system. This is a function from the set Zn star to Zn star, and how exactly is this function defined. So, imagine you have a public exponent E, this is not the identity element, this is some notation, this is an exponent E which we are going to use in the function, and this exponent E is relatively prime to phi of n. I stress it is not relatively prime to n, it is relatively prime to phi of n. Now, since E is relatively co-prime to phi of n, it will have a multiplicative inverse. I called that multiplicative inverse as D. So, since E and D are multiplicative inverse of each other, this relationship hold. Now, the RSA function in the forward direction is the following. If I want to compute the output of the RSA function for x, then that is same as computing x to the power e modulo n, right. So, remember x is a member of Zn star, and hence x to the power e modulo n will also be an element of Zn star, because my underlying operation is multiplication modulo n and x power e is like performing the group exponentiation. Whereas, my reverse function from Zn star to Zn star will be the following. If I have a value y and if I want to invert it, I compute y to the power d modulo n. So, I can prove that the function f d in the reverse direction is actually the inverse of the function f e in the forward direction, and the way we can prove this is as follows. So, you take any arbitrary x, and suppose for that arbitrary x the forward direction function gives you the output y. So, y is equal to x to the power e modulo n. So, what I have to show is that now if I invert this y, namely x to the power e modulo n, as per the inverse function, I should get back my x. So, let us do that. So, let us try to invert the value y. So, let me write down the value of y. Y is nothing but x to the power e modulo n, and then whole thing raised to the power d. Then I can apply the rules of group exponentiation and say that this is nothing but x to the power e d mod n, and remember that x to the power phi of n is 1, because x is an element of Zn star, that is what we discussed in the previous slide. So, x to the power e d modulo n will give the same answer as if x to the power in the exponent I do e d modulo phi of n, that means I can reduce the exponent itself modulo phi of n, but e d modulo phi of n is 1, that means this e d modulo phi of n is 1. So, this is nothing but x to the power 1 modulo n, and which is strictly x, because if x was a member of Zn star, that means x was strictly less than n. So, if x is strictly less than n, then the effect of mod will not take, and x modulo n will be same as x. So, that shows that these functions f e and f d, they are inverse of each other. Okay. So, if you go to the forward direction through f e, you can always come back in the reverse direction through f d. Now, based on all these things, let us introduce a computational problem which we believe to be sufficiently difficult, which we believe is really difficult to solve. It is like your discrete log problem. So, we know that there are certain groups where solving discrete log instance is really difficult. In the same way, RSA introduced a computational problem which we believe to be difficult to solve. Difficult to solve in the sense, in reasonable amount of time or practical amount of time we may not be able to solve it. I am not saying it is impossible to solve it. You can always solve it by doing a brute force, but the brute force algorithm will take enormously large amount of time if we operate on very large numbers. So, the problem instance is as follows. So, we first define what we call as RSA parameter generation algorithm. So, this is parameter generation. So, to generate the parameters, we randomly pick some n bit prime numbers p and q, and then we compute the modulus, which is the product of p and q. We compute the value of phi of n, we compute the value of phi of n. So, since n is the product of prime numbers p and q which are distinct, we will be okay. By the way, we will ensure that p and q are distinct. So, if p and q are distinct, the value of phi of n will be the product of p minus 1 and q minus 1. We will pick an exponent e which is co-prime to phi of n, and since e is co-prime to phi of n, we will be able to compute its multiplicative inverse modulo phi of n by running extended Euclid's algorithm. And finally, the output of this parameter generation algorithm is the modulus, the prime factors of the modulus, the public exponent e and the secret exponent e. What do I mean by public and secret? It will be clear soon. So, the RSA problem is the following: if I give you the modulus, but not its prime factors, and if I give you the public exponent e, in that sense it is public, it will be known to you, and it will be known that how exactly these parameters n and e are generated. What will not be known to you are the prime factors of n, and if the prime factors of n are not known, you will not be knowing the value of phi of n, and if the value of phi of n is not known to you, you will not be knowing the value of d. So, d is not known, phi of n is not known, p and q are not known. Now, the problem instance is the following: I will be giving you a random element from my group z n star, and your goal will be to compute the inverse function, output of the inverse function that we had just seen for the randomly chosen y. Namely, your goal will be to compute y to the power d modulo n, where d is not given to you, and y to the power d modulo n is nothing but computing y raised to power 1 over e, where 1 over e is not numeric 1 over e, but it is actually the multiplicative inverse of d. So, multiplicative inverse of d is nothing but so d and e are they are multiplicative inverse of each other. So, computing d is nothing but computing y to the power 1 over e. Okay. So, basically I am asking you to compute the eth root of y modulo n, and I want you to solve this problem instance in polynomial of n number of time, where n is the number of bits that I used to represent p and q. That means, my p and q are n bit numbers. Okay. So, one way of solving this problem instance is that you are able to factorize n. So, suppose you are able to factorize n in polynomial amount of time, namely you are able to compute p and q in polynomial amount of time. Once you are able to compute p and q, you will be able to compute phi of n easily, and since you know e and if you know phi of n, you yourself can run the extended Euclid's algorithm and compute d in polynomial amount of time, and then you yourself can compute y to the power d. But it turns out that factoring very large numbers is believed to be an extremely hard problem, right. Specifically with the current computing power, if I select my p and q to be as large as say 512 bit prime numbers, then my n will be an extremely large modulus. Then factorizing that extremely large modulus will be a very time consuming process, and hence you will not be able to solve a random instance of the RSA problem. So, now based on whatever theory we have discussed, let us see the concrete steps of the RSA public key crypto system. So, remember we have a function in the forward direction from z n star to z n star, namely x power e modulo n, and the reverse function is y power d modulo n, And we also have discussed the RSA problem, where if I do not give you the value of the secret exponent d, then computing y to the power d modulo n is very time consuming. That is what is the general belief. Now, the way RSA crypto system works is as follows. So, remember there is a sender and a receiver. So, what receiver will do is the following. Receiver will run the parameter generation algorithm, namely it will pick a random prime number p, a random prime number q, will compute its product, will pick an index e, which is relatively prime to phi of n. So, he can compute phi of n because he himself has picked p and q, and once he has picked e, he knows phi of n, he can compute d as well, and then he will set pk or the encryption key to be n comma e, and he will set his decryption key to n comma d. So, d is kept with himself, e is made public, and n is also made public. If there is a sender who has a plain text m and which it wants to encrypt, then encryption of m is nothing but computing the forward direction function as per the RSA function, namely just output m to the power e modulo n. And if there is a receiver who obtains the ciphertext c and who has the secret decryption key d, then to get the ciphertext, then to recover back the message encrypted in c, he has to basically compute the inverse function for this c. Inverse function is computable if d is available, and if d is available with the receiver, he can easily compute y to the power d modulo n and get back the message. Okay. Now, why this is called as a textbook crypto system? Because this is not precisely the way we use RSA public key crypto system in practice. There are lots of shortcomings. One very important a very bad feature of the way RSA crypto system is proposed is given here, and if I use here, the major shortcoming here is that it is deterministic. It is deterministic in the sense that if there is a sender S and suppose he wants to send the same message m after every 1 hour, okay, then if he encrypts the same message m using the public key n comma e, every time he will be producing the same c. So, the first time he wants to encrypt the message m, he will send c. Next time he wants to send the message m using the same key, he will be again sending the c. Again next time he wants to send the same message m, he will be sending the c. This itself is a lot of information for the third party or the attacker. He may not be able to learn the exact value of the message m, but he will be coming to know that actually it is the same message m which has been encrypted and communicated to the receiver, and depending upon my underlying application, this itself can be a breach of security. Ideally, I am looking for a process where even if the same message m is encrypted using the same public key multiple times, it should produce different ciphertexts with high probability. But that is not the feature available with the way RSA public key crypto system was invented, but we can of course get rid of this shortcoming, and the actual way with which in which we use the RSA public key crypto system is different from the way it is proposed here. But this forms the basis of the RSA public key crypto system, a very interesting public key crypto system. So, with that I conclude today's lecture. Just to summarize, in this lecture we discussed about public key crypto system, and we discussed two popular instantiations of public key crypto system, namely we have discussed ElGamal encryption scheme and we have discussed RSA public key crypto system. Thank you.